We're going to give a name to the slopes of the tangent lines. And the name of the slope of the tangent line, one way we can think of it anyway, is we're going to call it a derivative. So the slope, got the word up here, but the slope of the tangent line at any particular x value, that's going to be what we are going to refer to now as the derivative of whatever function is, function f. So the slope of the tangent, also known as now derivative of the function f. So those two are one and the same. Derivative is what we've been terming the slope of the tangent line. Now there's some notation that goes along with this derivative. The notation for derivative function f, is we're going to put a little mark alongside the f there that designates the derivative of function f. Now, we can say, that's a derivative, but sometimes we shorten it, we say that's f prime. So f prime is maybe how we read that, but technically speaking, what it means is, it means the derivative of f, which means the slope of the tangent line of f at any particular x value that we're talking about. And so where we're going to start with this is we're going to start with getting derivatives from the graph of the function, because that's kind of where we're starting here, the graphical definition, if you will, of the derivative. And so I'll give you that handout there. You give myself one, so I refer to here, draw it up here. Yeah, so let's go to graph 1 there. And on graph 1, do a couple of derivatives. We don't know the equation, so that's we just call it y equals f of x. So what we're going to do, starting off here with these derivatives, is we're going to estimate some derivatives. And so the first one, let's do on graph number 1 here, is let's estimate f prime of 3. F prime of 3. So put the parentheses with it and then the number in there. That just designates, right, the x value. We're talking about the x value 3. So we're going to go to x value 3, and we're going to try to estimate f prime off of that. Well, by what we know so far, we know that this is the derivative, and the derivative is the slope of the tangent line. So that's what I'm looking for here. I'm looking to estimate the slope of the tangent line at 3, x equals 3. That's what this means. F prime of 3 is going to be the slope of the tangent line at x equals 3. All right, so where are we located on the graph? Well, 3 looks like it's over somewhere about in here on mine. Yours is a little more accurate, but yeah, so I'm coming down, so I've got the point on the graph is there, but that's not what I want. I want the slope of the tangent line. And so estimate here, and so again, we may have done this once or twice, just drawing a tangent line there at 3. To the best of your ability, the tangent just kind of comes along and skims along the graph, right? That's what the tangent does. It just kind of skims along. We found tangent lines like this all along, but now we're not really finding, we're just estimating its slope. So I want to estimate the slope of that line. That's what f prime of 3. So f prime of 3 is going to be the slope of this line. Now, there's a couple ways we can do that. We can figure out, well, if I rise 2 and run 3, here's the way I like to do it. Because the way I'm going to do this is I'm going to do it as a rise over run. And I like to get this derivative, since that's another way to find slope there. I like to do it let's just fix it, always do a run of 1 and then see what the rise is that goes along with that. You with me there? Well, you don't have to do it that way. I mean, you can say, well, if I rise 2 and run 3, or it works. But I like to always say, let's do a run of 1 and then see what the rise is, and that's going to give me my slope. And that's going to, so thus it gives me my derivative. All right, so if I draw mine in, I'll do it on my paper here so I can again, see what you get, and I'll see what I get. All right, so if I do tangent, and run 1, okay, so I see what I'm going to say. What'd you get? I mean, it's approximation, so you don't have to get the same thing I do, but about what you get. 1.5? Yeah. Around there? I mean, it doesn't have to be exactly that, but that's what I'm seeing. Yeah, because it runs 1, and then the rise here is 1.5. Yeah, that's what I got. So the rise is 1.5, and then, so thus, that's going to be my derivative. It's about 1.5, because that's the slope with 3 halves. I mean, something around there, because this is just an estimate. I mean, you shouldn't get a negative value because it's not, slope downward, but if it's in the ballpark, you're okay. 1.5, 1.6, 1.4, you can be close, all right? So yeah, but now, instead of calling that the slope of the tangent line, we're now calling that the derivative at 3. Okay, same thing. All right? So number 2 here, let's estimate f prime of -1. And that's approximate, I guess, I should say, approximately. Because we don't know the function, so we can't really get an exact value. But so f prime -1, same thing. Come over here at -1, is that the, that's the, right here at the x-intercept. Now, one thing we can see about that, if I draw that in as best I can, one thing you can see about that is that going to have positive or negative slope? Well, it's going downhill, isn't it? So it should have a negative slope, so that's one thing. Quick check. All right, so how am I going to do it? Well, again, however you want to. Let me see what I get. Drawing a negative tangent line there. So if I run 1 down, I'm looking, if I do a run of 1, so that would be this way. The rise is -2, that's what I got. So it's down 2. Is that what you see? About? So it's about a negative, the derivative there is about a -2. With me? All right, one more. This one's actually be a little easier, but it is an important point. F prime at 1.5. Approximately equal to what? And I might can remove the approximate here. What did you get there? Where am I at if I'm at 1.5? Well, the point is, it's right here, isn't it? 1.5, I'm down here, right at that low point. And so if I do a tangent line there, what have I got? Because the derivative is the slope of the tangent, here's the tangent line. So what's the slope of that line going to be? It's horizontal, isn't it? What's its slope? Slope of horizontal line, it's 0, isn't it? Yeah, since I've got a horizontal tangent line, the derivative, and that's what I was saying, I could remove this because it's exactly equal to 0. Whenever you have a horizontal tangent line, your slope's going to be 0. And so thus your derivative is going to be 0 at 1.5. Okay? And that'll be an important point in a lot of context. But yeah, if I've got a horizontal tangent line, you got a slope of 0. So any point like that where you draw the tangent line and it's horizontal, your derivative is going to be 0 at that point. Okay? So at horizontal tangents. Slope is 0, so the derivative is 0. Because there's no slope. Slope is 0, so derivative is 0. All right, with me on that. Now again, well, all right, we'll do that in a second. All right, number 2. Okay. Another, I think I mentioned this back in the first unit, but this will help us with the next thing we talk about. The other thing to consider is, the derivative is the slope of the tangent line. But another way we can think of the derivative, the slope of the tangent line, remember we also said we could not only think of it as the slope of the tangent line, but we could think of it as the slope of the curve at that particular point. Now, if you've got this parabola here, the slope's changing as you go around, right? Because it's -2 here, it's +1.5 here, but at that particular point, we can say the slope of the curve is -2. The slope of the curve here is 1.5. So it's just another kind of way of thinking. I mean, it's practically the same thing, but instead of thinking of the slope of the tangent, just think of the slope of the curve. Because around that, there's not much distinction between the graph and then the line here. It's pretty indistinguishable there. I mean, it's tangent, but it's pretty indistinguishable. So that's another way to think of it. That'll help us on our next example here on number 2. If we think of it in those terms. So let's go on to number 2 here. Number 2. Number 2, we've got just a straight line. Try to get it kind of accurate here. Okay. So let's do the same thing here. Let's estimate. I call this one G, didn't I? Y equals G of X. So I've changed the name, but guess what? So if I want to estimate on number 1 here, G prime of 2. G prime of 2. Well, now we've got a derivative of G prime. It means the same thing. It means the slope of the tangent line at 2. Okay, so at 2 here, where am I? Right about here? Well, yeah, when you're doing tangents of lines, that gets a little tricky. Maybe that's not the right word, but that's why I was saying, if you think of the slope of the tangent to mean the slope of the curve at that particular point, that helps you to think of this. So this is the slope of the tangent, but also means the slope of the curve. What's the slope of this curve? Well, it's a line, and so it has a constant slope. Yeah, I can just think of this as the slope of this line in this particular case. What's the slope of this line? Well, if I do my run of 1, what's my rise? I think it's 1, isn't it? 1 to 1? Yeah, I think you got a slope there of 1. Thus, the slope of the line is 1, the derivative of at 2 is 1. Okay? Because that's the same. Those two are this one and the same. All right? Now, the good thing is, when you've got a line, if I do g prime of -1 now, what's g prime of -1? So if I come over at -1, it's going to be the same, isn't it? Because it's constant. We got the same, it's the same line, it's the same slope. So g prime of -1 is 1. Any derivative there that you can come up with, g prime of 3 is 1, g prime of 30 is 1. Yeah, but if you've got a line, the derivative stays constant because the slope is constant, okay? So for the derivative of a line at any point, or at any x value, the derivative is constant, it stays the same. Okay. So if you got a line, if you get the derivative at one point or one x value, then it's the same for all the other x values. It stays the same. So if the slope here was -2, then the slope at the next one's -2. So for a line, it's just going to be a constant number. All right, it's just the slope of the curve. All right, with me there? Okay. So the third one, any questions on that? Is that okay? All right. So on the third one, let's do this. Let me draw it up here. So I got this. Sort of like that. Negative one's here, positive one's here. It's a 2. Yeah, all right. So here's what I want us to do. List in increasing order the following. Okay, h prime of -1, h prime positive 1, h prime 2, h prime 5, and then h -3. And that last one does not have the prime, doesn't have the derivative symbol, and that's not on accident there. List those in increasing order. So in other words, start with the smallest and then go to the largest. I'll give you just a minute to come up with an order here, and I'll do my order. Take a minute. Put those, start with the smallest, which obviously is going to mean most negative in this particular case, and then see what you get. So probably, kind of estimate each one as you go, maybe. Okay. Which one should be the first one? If I start with the smallest, meaning in this case probably most negative. Well, the way I see it is there's only two of them that have negative values. This one's negative. How do I know that? H prime of 1. Well, H prime of 1 is the slope at 1. And isn't that going to be a negative value? It's a negative value. The other one that's negative here, well, the slopes at the other ones, I don't think I have any other slopes that are negative, but on purpose I did this one, and that's h of negative 3. What's h of negative 3? Well, that's the y value at negative 3, not the slope at negative 3. It's the y value at negative 3. And if you go down to the y value at negative 3, you have to go off of this graph a little bit, but it's going to be down here somewhere. And so that y value, I'm going to say, what, maybe negative 10-ish, okay? The slope at negative 3, it's a positive. But that's not what this asks for, is it? So you got to be careful that, you know, we're talking about derivatives, but there's still h values or function value. And that's what this means. It's the y value. The slope here is positive, but this has a y value that's negative. And so I believe that's where we start, wouldn't it? Because it's around negative 10. I estimated here that's approximately negative 1.5. Like I said, that's negative 10. So I'm going to go with h of negative 3. You with me there? It's more negative, so it's smaller, the smallest. And then I'd go with the h prime of 1. All right, now what? Which one would go next? Well, those are only two negatives, but then I have a 0 one, don't I? Which one's 0 of the three that remain? Isn't h prime is 2, 0? Why? Well, if you draw, that's talking about the slope of the tangent line. So if I do the slope of the tangent line at 2, I got a horizontal tangent line, that's 0. Slope of that's 0. So it would go in the third slot because the other two are positive values. H prime of 1, h prime of negative 1, maybe I did it here. H prime of, that's the h prime of negative 1 is talking about the slope at negative 1, and I estimated around 1.5 for its slope. And then I didn't really get to do h prime of 5 because h prime of 5 out here, it's way off the graph. But you can see there, hopefully, that it's a large positive slope, isn't it? Because that thing is up here, and so it's got a large slope to it because it's going to have if you do a run of 1, it's going to have a large rise. So this is a large, let's just call it a large positive slope, or large positive derivative. So between h prime of negative 1, h prime of 5, the next one in increasing order will be h prime of negative 1, and then h prime of 5. Question about that, does that look okay?